And I heartily welcome our head of the department, Dr. M. Satish Reddy sir. And also, I heartily welcome our beloved principal, Dr. Naveen Kilari sir, and our chairman, who has arranged this wonderful session, Dr. K. Chandrasekhar Naidu. Our main agenda of this program is to know the importance and various techniques adopted in the geotechnical field. With this note, I would like to invite our principal, sir, Dr. Naveen Kilari, to say a few words about this program.
Thank you, Sarumati. Outset, the honorable resource person, he is not just a resource person, he is one of the renowned, learned, erudite personality in the entire India, especially in the civil engineering arena, Professor K. Nagendra Prasad sir. Really, even I feel honored to get to share a few words about the Professor Nagendra Prasad sir. Such a high versatile professor he is. Really, even I am very fortunate enough, sir, to have an interaction with you in my entire career. And so really on behalf of the WAMU Institute of Technology, though you are a family member of the WAMU family, still we are extending a warm invitation to you, sir, for this 3-day webinar on the recent technologies in the geoengineering. I know that you are very senior to me in the WAMU Institute of Technology. I am only just 2 years old at the WAMU Institute of Technology. You know the right from the soil testing, you know the foundation stone of the WAMU Institute of Technology also. So I am an earthworm in front of the king cobra like you. So as you know each and everything of the WAMU Institute of Technology. But however, so once again, on behalf of our chairman, on behalf of our WAMU family, once again, I am inviting you. And also we are so much thankful to listen, to have such a wonderful session by a very learned personality like you. And also with your permission, I would like to share a couple of words with our students also. So actually these students have joined very recently under the lateral entry directly into the second year. So hello, my dear students. I too welcome you all to this to the WAMU Institute of Technology. I appreciate you. I congratulate you for joining BTech Civil Engineering program at the WAMU Institute of Technology. I am sure that the WAMU Institute of Technology is going to be a very good platform to provide you a plethora of the opportunities to showcase your talent and also to get your skills enriched so that you can get very good job opportunities. One thing I would like to share with you that definitely, irrespective of the branch, whether it is a civil engineering or mechanical engineering or electrical engineering, whatever it is, if we have the core knowledge, if we have the knowledge, number of jobs are there. There is no unemployment. There is no unemployment. There is unemployability is there. It means nowadays, across the India, across the world, there are number of job opportunities. Even if you take the civil engineering, geotechnical, GIS, remote sensing, everywhere, number of jobs. But only what lacking is, there is no ability to do the job. Unemployability is there. So that's why, my dear friends, I think now it is not the right time to speak about all these things. Why? Because we are having a very big, gigantic person in front of us now. So we have to listen more from him. So definitely I will make my time to interact with you on some other day. But however, just now we started with this one, and also in the coming week or in the coming days, still on some more on the structure, the recent advances in the structural engineering. Already we are inviting one senior professor from JNT Anantapur, Professor Sudarshan Rao sir. So like that, we are arranging an array of expert lectures. So to know what is happening in the civil engineering, so please make use of this opportunity. Please get acquainted, please get acclimatized with the latest technologies, what is happening in the civil engineering. So, sir, once again, I thank you for accepting our invitation and going to share your entire experiences with our students, sir. Thank you once again. And I appreciate the HOD, the young and dynamic HOD, Dr. Satish Reddy sir, for coordinating this program. And also I thank Saurumati for giving me this opportunity to interact with the students and with the big personality, Professor K. Nagendra Prasad sir. So thank you, sir. Thank you.
Thank you, sir, for your wonderful speech. Now, I would like to invite our HOD, Dr. Satish Reddy sir, to speak few words about this webinar.
Good afternoon to everyone. I welcome all to 3 days webinar on importance of geotechnical engineering in engineering practices. First and foremost, I thankful to Professor K. Nagendra Prasad sir for accepting our invitation in his busy schedule. Sir, we are very much thankful for you, sir. From the department side, we are very much thanks, sir. Geotechnical engineers are responsible for evaluating subsurface and soil conditions using the principles of soil and rock mechanics. It is very much necessary to determine whether the particular site is suitable for proposal project and can inform the engineering design process with regard to how the ground conditions can be made safe and effective for construction purposes. So I hope this session will be more informative and provides you great knowledge in the field geotechnical engineering. With this note, I hand over the session to Sharmati madam.
Thank you, sir. Now I would like to introduce our speaker, Dr. K. Nagendra Prasad sir, the professor and chairman, Board of Studies from SV University. Is presently working as professor and vice principal in SV University, Tirupati. He has completed his PhD from IISc, Bangalore. He worked in various positions such as head of the department, chairman board of studies for undergraduate. He has also served as a visiting professor in South Korea. To his credit, he has received state awards, the Engineering of the Year 2011 from the Government of Andhra Pradesh and Institute of Engineers, India. Another state award from the Best University Teacher from Higher Education in the year 2010 from Government of Andhra Pradesh and again in the year 2015 by Vidya Parirakshana, and finally as an Eminent Engineer Award in the year 2017 from Institution of Engineers. He has also published over 100 research papers and handled 6 research projects. He has done her research collaboration with IISc Bangalore, South Korea, Germany, and USA. He has guided 16 doctorates, and there are 5 ongoing research works as of now. Apart from that, he is the chairman for Indian Geotechnical Society, Tirupati, chairman for Institution of Engineers, Tirupati. With this brief note, I would like to hand over the session to Professor Nagendra Prasad sir.
Thank you so much for fantastic words from the principal and the head of the department and also Sarmati. It has been my pleasure interacting with students all my career. I delivered more than 125 invited lectures across the globe and very busy consultation work I have done in this region, spreading about 3,000 projects. I think it has been a very nice experience for me, and I thank my university for having provided me a lot of opportunity to actually know about the practical problems outside the campus. And then I found ways and means to translate whatever that we read in theory to practice because of this consultation work. Apart from that, I also worked as placement officer at SV University and enabled a record number of placements. And then I came to know what are the attributes of a student and what are the various things that students have to possess in order to make their careers meaningful. And then all these opportunities I have got by standing in Venkateshwara University campus. I have developed a lot of collaborative works with Korea and then Germany, published many papers there. I also worked as visiting professor at South Korea, Dongye University, South Korea, and then try to understand the problems related to sample disturbance. Sample disturbance used to be a major problem for them because they have very deep deposits of soft clay, and they are constructing huge infrastructure projects on very thick soft clay deposits. Then they had the problem of the sample disturbance. Once you introduce the sampling tube into the soil, entire soil will get disturbed. So true characterization of soil used to be difficult. Then I have given some mathematical formulations as to how this sample disturbance can be sorted out by introducing different thicknesses of sampling tubes into the soil, and gave a mathematical expression so that without disturbance how the soil sample properties will be there. And I could publish some of these works in Geotechnical London, one of the top journals in geotechnical engineering. 3-4 papers I have published in Geotechnical London. On this occasion, I also find Raghupati Manohar Reddy, my research student, is also there on the screen. He is presently advisor to the Honorable Chief Minister on technical issues. He did his doctoral degree under my guidance, and he has contributed quite significantly for the infrastructure development of roads and buildings department. Welcome, Manohar Reddy. I'm happy that I'm seeing you on the screen, and you can also interact with me as and when I'm proceeding with my topic. And as principal sir, you can formally invite Professor R. Manohar Reddy, one of the very distinguished engineers who received many distinctions and awards. And if time permits, he is also from Chittoor district. You can invite him sometime to your institute, so that he has actually done the PV Narasimha Rao State Highway complete from concept to design, and also now it is under execution. He has delivered similar lecture at our university, which was actually received by the students very well. I request Dr. Satish Reddy and the principals to formally invite R. Manohar Reddy, Dr. R. Manohar Reddy, the advisor to on technical issues to present government to the gathering.
Sir, good afternoon, sir.
He is the principal.
Sir, your mic is on mute, sir. Please unmute yourself, sir. Sir,
Okay.
good afternoon, sir.
Good afternoon.
Sir, I am Naveen, sir. I am Naveen, sir. I am the principal, Wave Minister of Technology, sir.
Yeah, one of your promoters, Nagaraj Naidu, is now known to me.
Sir.
He also invited me for a meeting. I will try to come sometime later.
Sir,
And
we are extending a cordial invitation to you, sir. Please, sir, definitely we will. Please try to interact. Please make your time for 1 hour. Please interact with our students also virtually.
Sure.
Sir.
So, thanks. Thank you, principal, for doing that. I now, because of paucity of time, because our time slot is limited, I just would like to proceed with my topic, and I'm just sharing my screen, and all of you can see. I think. Please give me permission for sharing the screen. I think you are able to see the screen now. Someone can react. I think you are able to see the screen now.
Yes, sir. Yes, sir. We can see the screen, sir.
Okay. Now I am proceeding with my presentation. This is the first webinar on importance of geotechnics in civil engineering practice, and being delivered at WEMU Institute and under the auspices of WEMU Institute of Technology near Pakala, Chittoor. I just would like to say that the importance of geotechnics in civil engineering practice assumes a lot of importance, and you will realize as I am proceeding with my lecture and how this importance is gaining a lot of ground and what kind of actually impact that is creating all over. And I just would like to start by saying that though it does not matter how many resources you have, if you don't know how to use them, you can see here there are a lot of resources here. He has stamped on that and looking out of the wall that he is not able to use these resources. Similarly, in life we have got lot of resources at hand, but we really many a time we fail to manage these resources. The entire art of living lies in trying to utilize the resources that are available around us. I just would like to start my presentation by saying that soil is a particulate material. Suppose if you take steel, for example, steel has a lot of intermolecular attraction. The molecules are so strongly bonded, it behaves as a single body. And when you apply the load, all the molecules, all the particles which are making iron as a body will act together. But if you consider soil, it is completely a particulate system. Suppose you consider the example of a gravel. You can see that gravel looks like that as individual soil particles. And if you take the case of sand, for example, sand you can take into your palm and then drop as individual particles, and you can see that sand is also a particulate system. And if you take clay, for example, the silt is, we know that all of you must be knowing that soils are classified into two major categories. One is coarse grained material, the other one is fine grained material. And once you are able to classify the soil into coarse grained material or fine grained material, 50% of your problem is solved, in the sense that the coarse grained materials, we actually have different techniques to adopt in trying to provide solutions for the foundations. And if it is clay soils or fine grained materials, we have altogether different set of methodologies that we adopt for clays. So in the hierarchy, if you consider, the first thing is gravel, next down size is sand, and after the sand size, it is silt. You can also see that silt is also a particulate material. We can actually see the silt forming into a heap when dropped from a particular height. This is also clay falling apart here as individual particles. And both silt and clay, they come under fine grained soils. Why they are classified as fine grained soils? As entire world, if you go to Purdue University or if you come to Venkateswara University or any university, the descriptions are same. That means soils are classified in a uniform manner. Whatever the particle size you are able to see with your eye, that is minimum particle size which you are able to see with your eye, that part of soil is called coarse grained material. That means if you take, for example, gravel, you can pick up one single particle and you can see the size. If you take sand, for example, you can pick up individual soil particle and see the size. But in case of silt and clay, the particle size is less than 75 micron sieve. That means 75 micron, that is 0.075 mm. That is the size of the particle of silt and clay. And any particle size less than 0.075 mm, your human eye cannot detect. That means the limitation of the human eye to detect the individual particle size is 0.075 mm. So any particle size greater than 0.075 mm is called coarse grained material. Any particle size less than 0.075 mm is called fine grained material. In fine grained materials, we have silt and clay, and this clay size particle is still less, 0.02 mm, very, very, very small size, and that makes actual clay. And the silt and clay, they behave in a different way as compared to sand and gravel. I just would like to give you an example. For example, if you take gravel, the gravel which I am showing here, if you take a pinch of gravel and then drop it through beaker full of water, you take a beaker having water full 100 ml water jar and then drop. Then what happens is within no time, all the particles will drop under the influence of gravity. Within beat of eyelash, all the particles will come down. That means it is a gravitational material. Gravel is a gravitational material. For example, if you take sand, sand also, if you take pinch of sand and put it in beaker full of water, then sand also within no time will go and settle down. That means sand and gravel, their characterization are governed by gravitational forces. That is the reason why when you are encountering sand or gravel in the field, we have to actually use vibrator and see that the soil, gravel or sand, they get settled down. I will tell some of the practical examples little later. Just to try to understand that these two are gravitational materials. Very simple experiment of dropping a pinch of these materials through beaker full of water will demonstrate that all particles will settle down and they actually, the characterization is under gravity. For example, if you take silt, this material, and put it in measuring jar full of water, then what happens is soil particles will not immediately go down, but there will be some kind of Brownian motion will be there. Particles will be experiencing chance collision, and these particles form into a bigger size particle, and then they fall maybe after half an hour or 15 minutes. That means it takes some time for silt material to drop down in measuring jar having water. Suppose if you take clay, for example, and put small powder of clay into the measuring jar, then all particles will go into Brownian motion. They experience hither and thither, to and fro motion, and they will be in that kind of Brownian motion for considerably long period of time, maybe sometimes depending upon the clay mineral. So if it is of Mont Morlite, it will take 24 hours time to settle down. That means they are not gravitational materials. They are having surface interactions. That means surface forces are predominant, and therefore silt and clay, when you are dealing with these materials in practice, then we have to be very, very careful. And then we have to use this chemistry, that is soil water chemistry concepts into picture. And when you are encountering silt or clay, altogether different kinds of methodologies we have to adopt. Because you can see here, this is the clay material. It goes on absorbing lot of water, and then after some time the solid state enters into plastic state. Even if you are more water, it will be in plastic state up to some limit. Afterwards it becomes liquid state. That means depending upon the moisture that you are adding, sometimes at lower moisture content it behaves like solid, and after some moisture content it behaves like plastic material. After some more moisture content, it actually goes into liquid and then starts behaving like liquid. That means these materials, depending upon the access that is given to water, their behavior will turn out to be, and through different phases it passes. One is say solid, semi-solid, plastic, and liquid state. And therefore, depending upon the boundary conditions, depending upon the accessibility to water from nearby source or groundwater table rising up, these materials completely behave in different way because of soil water chemistry. Soils, there is surface interactions, they become predominant, not gravitational material. Suppose if you introduce water into gravel or sand, water will percolate and go down, and it does not actually affect the behavior of material as significantly as water does in case of clay. You can see here it now almost it has become moldable plastic state. Still, if you add more water, it becomes liquid. That's what I just wanted to impress upon you, the fact that soil is a particulate material. Therefore, unless and other and unlike other engineering materials, for example, steel or wood or aluminum or any other concrete, even concrete is also a particulate system, but it is adhered and it is actually bonded together by cementation component. But soil particles are completely particulate system. It has got voids in it, and it has water also will find place in it, and therefore it gets into complex system of three phase. And therefore understanding soil as engineering material is completely different from rest of the engineering materials which behave coherently in a completely different form as compared to the soil, which is a particulate system. I just said some kind of model I have put here. Suppose you take a container and imagine that the spherical balls are kept one over the other. You can see one particle over the other. It is kept there and it is closed. A lid is closing that. Suppose if I keep this weight on that, then what happens is the original position is now gone down below, and this particle will go and occupy in the valley that is there here. This particle will go and occupy the valley here, and this top particles always will go because of the load that you are applying, because of gravitational effect and point to point interaction effects. These particles will compress, and you can see that there is some compression that is taking place, and voids also getting reduced here. And this again indicates that these materials are particulate in nature. And if a confinement is not there, for example, if the wall is not there, all particles will roll down under the influence of gravity. That means this small experiment also will demonstrate that it is a particulate system, particularly gravel and sand. They are all governed by gravitational forces. If the confinement is not there, these particles will have a tendency to roll over one another, and then complete flow will take place. And the settle, suppose if the weight is looked down upon as a structure, it will settle if there is no proper confinement. So even if sand is there, we have to actually keep it at a depth sufficient that the overburden pressure is taking care of lateral confinement of the soil. So just before introducing soil, I just wanted to tell you that it is a particulate system, and therefore lot of complexity is associated, and the complexity is compounded by particle sizes, particle shapes, and there are many other geometrical features, and the engineering, the architecture, all these things will come into picture. Therefore, we have to very, very carefully understand soil. And once you understand it, it has got a language to speak. And if you understand the language with which soil is speaking to you, then you will be able to easily provide solutions to soils whenever you are encountering. There it is said by Atkinson, one of the major former professors of Cambridge University, that all structures except those which actually float, all are founded in soil. Therefore, whatever the infrastructure projects that you are seeing, they're all founded in soil. When once you are doing this foundation work, and you have to understand the soil and how it is going to behave under the influence of loads. And soil can be tested in the laboratory, and it has got a language to speak. And then if you can understand that language, you will be able to provide solutions with the language that soil is speaking to you. So it is said that a wise man always learns from mistakes of others, and nobody lives long enough to make them all. This is a famous saying. That means, suppose if I make a mistake, I have to declare to my fellow engineers that I am doing a mistake, so that my fellow engineers will not commit the same mistake. Therefore, always we should be wise to understand the concepts from the experiences of others, either by one-to-one interaction, or by reading books, or by communicating with the persons outside. We can learn what is happening, and that forms a basis for understanding of the different materials. I just would like to introduce to you this famous man, the Carl Terzaghi, and he is recognized as father of soil mechanics. And he actually, when he published the book He was actually 1883 to 1963. When he published a book in 1925, that became the starting point of the beginning of soil mechanics, and that's why he is called father of soil mechanics. And he actually made principal contributions in the field of soil mechanics during those days. He used to go by boat and by ship from place to place wherever there were problems related to soil, and then he devised means to provide technical solutions with proper scientific backup, and he postulated many theories, which theories are basis even today for us. As you get along with your subjects, you understand the basic work was done by Carl Tesge in formulating lot of theories based on which we can take lot of decisions. So this entire soil mechanics as a subject began to be understood from the year 1925 when Carl Tesge made his first publication in German language. So he has said some one or two sayings, because I keep saying what Carl Tesge said at many places. In Carl Tesge at Harvard, he said that the one thing in simple words, because a lot of text is written here, I would like to simplify it by saying that if you want to know whether the soil is actually what type of soil it is and how it is going to behave, Carl Tesge says, you take the soil to your hand and feel. Once you have that feel, then you will be able to comment on what type of soil it is. Don't look at soil and say, this soil is so and so and the other soil is so and so. You take the soil to your hands. If you feel grit, then it is silt. If it is smooth, it is clay. While interacting with water, when it sticks to you, it is again plastic clay. And once you feel the gritness and size, and you will be able to understand what the material is that you are encountering in practice. That is what is very important. And he has drawn an example. For example, if you want to see and understand the comfortableness of a chair, if you want to understand whether a given chair is comfortable or not, can you see the chair and say it is comfortable? Can you see the chair and say that it is comfortable? No. You have to be seated in the chair and try to see whether the chair is comfortable or not. Therefore, whenever you go to field, feel the soil. Take the soil to your palm of your hand, and then you try to understand what type of material it is. That's what he said. The another thing he said is that engineering is a noble sport. All of us makes mistakes because somebody asks, I do not know, I don't have time now. I would have straight away interacted with my students, but I would like to ask you a question and give the answer also myself. Who an engineer is, according to you? Can somebody react? Who an engineer is? So an engineer is one who takes decisions, because many things are said. Engineer is one who translates theory into action. Engineer is one who makes actually theory to reality, and all those things are said. But according to me, an engineer is one who takes decisions in the face of reasonable evidence, in the face of the facts that are presented to engineer. He has to take decisions and go forward. In the process, sometimes we may take a wrong decision, but it does not matter. But you have to, an engineer has to take a decision and then go forward. By chance, the decision proves to be little problematic, or it is going to give wrong result, then you declare it to all your colleagues that this decision does not work, this approach does not work. So that once you declare that you are a noble engineer, even if there is evidence that you have failed, and if you say that I have not failed, but system has failed, that means you are not a noble man, you are not an engineer at all. An engineer takes decisions. Most often decisions will prove to be all right. In case if decisions are going to be otherwise, you declare that this decision doesn't work under existing circumstances, then what happens is the others will come to know, and then your actually the personality will be exemplified. That what the engineering is a noble sport which calls for good sportsmanship. Occasional blundering is part of the game. Let it be your ambition to be the first one to discover and announce your blunders. If somebody else gets ahead of you, take it with a smile and thank him. Once you begin to feel tempted to deny your blunders in the face of reasonable evidence, you cease to be a good sport. So I request all the students who have joined on lateral entry, they're all basically having diploma and they would have had a lot of practical experience and they would have been exposed to many civil engineering subjects. And tomorrow you are going to become a very full-fledged engineer. Please remember that you have to make decisions, and sometimes if you are wrong, please declare that the decision is wrong and doesn't matter, and that actually improves your personality. But only thing is you should never repeat that mistake. This is what some of the inspiration things that were said by Paul Tesagi. And the earlier, if you take the history of soil mechanics and foundation engineering, it was all completely based on empiricism. That means earlier it was completely based on experience, because Romans have built, Egyptian temples have been built, Romans built a lot of harbors, aqueducts, bridges, and other things since times immemorial, but they're all based on experience. And you can also see that leaning tower of Pisa. And somebody in future, on behalf of your civil engineering association, please take all the information from net or other resource available resources. You make a presentation, you give a webinar on leaning tower of Pisa yourself, and it was built in 14th century. And then recently John F. Burland, of whom I'm a big fan, and he is actually the person who solved the leaning tower of Pisa problem. And you can see that it was continuously leaning because it was laid on two differential platforms. That means soil having one properties on one side of the foundation, the compressible properties on the other side of the foundation, and then one side the entire piece or tower started actually sinking. And then you can see that it is out of plumb by 16.5 feet now, and Burland has found out that some water from nearby source is coming into the foundation soil and it is wetting the soil. And as you have seen, once clay becomes wet, it behaves completely differently. And therefore what he did was, in the ground, he has actually intercepted water coming into foundations of Leaning Tower of Pisa, and that's how the foundation became dry. Earlier, people have done a lot of grouting and other counterweight techniques, many techniques, but it never worked. But Burland found that there is some water that is leaking into foundation, and then he actually gave the solution. And now that at least at a particular rate of lean, the tower was leaning, now has completely been arrested by John F. Burland's intervention and the Imperial College London. You can also see a lot of presentations by John F. Burland, a great man in soil mechanics, more than 80 years old, still he's contributing quite a bit. And this is what the Leaning Tower of Pisa, and you can see that this is actually 3.9, 5.5 degrees. Earlier it was tilting, now it has come back to 3.99 degrees from the plumb. And you can, some of you can make a presentation on this masterpiece, the example of the compressibility of the soil. And the structure has not failed, but foundation started tilting, though therefore the soil which is below here, which is compressible, started sinking. Now it has been restored to a great extent. So Dr. Paul Tesgi, in his rankings lecture, he said that people normally attach a lot of importance to outward structure, the elegance of structure. I would like to give you example of Taj Mahal, and I think Bush has come, and then Obama has come, and Clinton has come and visited Taj Mahal. Almost all American presidents, they have come, and international tourists, they come. They only see what is the beauty, symmetry of the complete Taj Mahal, but nobody would ever think what type of foundation it has actually been actually made possible for that particular glorious structure, which has not actually experienced any cracks, though it was founded in the clay on the banks of Jamuna River in the deposit of silt by well foundations during that time. So Carl Tesge says that when you attach more importance to external beauty and don't attach importance to what is happening below the eye, that is in foundation, the consequences will be very catastrophic, and therefore we have to pay a lot of attention to soils and the foundation approach, the approach methodologies that we adopt in case of soils. And I just would like to present some of the case studies that I have done in the recent past in the region of Rayalaseema, just to impress upon you what is the importance of soil mechanics, what is the need for proper investigation of soil before taking engineering decisions. I just would like to, at a glance, would like to present some examples, and then I would like to go forward. And if you have any questions, students, you can ask me regarding whatever the subject doubts that you are having. You can also ask me some doubts, those who are interacting with me. I just, before going further, I would like to clarify the doubts if you have any, particularly in the subject of the foundation engineering. Any student?
Students, if you have any doubts regarding the foundation engineering, please ask.
Because you have entered civil engineering, which is a very noble profession. And then I congratulate all of you that you enrolled yourselves in WEMU Institute of Technology, and which has got all accreditations. And you are going to become future engineers. And if you have got any doubts regarding what kind of the subject that you are going to handle, and based on interaction that I have just now had, you can ask me. Otherwise, please quickly react. Otherwise, I will go forward with some, by compiling some of the recent experiences. There are many things to share, but I just would like to tell you, to present to you the importance of role of geotechnical engineering. There is one question, and sir, in the very beginning you said that silt and clay are not gravitational material. Can you justify that, sir? That is a wonderful question. I said that you take a pinch of gravel and put it in measuring jar full of water, either gravel or sand, within beat of eyelash, what the particles will go down into the bottom of the measuring jar. But if you take, for example, silt, a powder, silt means less than 0.075 mm size. If you take silt and put it in the measuring jar, it will not actually go as quickly as the other materials like gravel and sand. It will take long time. And all of you can do this experiment. As soon as you go back from the lecture, you take a mug full of water, whatever the soil that is around you, you take a pinch of soil and then dry soil and pour it into that. And then tomorrow when you see after 24 hours, you see that sand is there at the bottom, silt is there, gravel is there at the bottom, sand is there on the top of that, silt is there on the top of that, clay is there on the foremost layer will be clay, because that would have settled after 24 hours of time. So if you take sand to your hand and then you can feel the grit and particles will not stick to you. Suppose if you take clay and then it will smear. Suppose if you take little moisture in your hand, it will actually smear in the palm of your hand. That means it is not gravitational. It is a sticky material. It has got surface interaction. Each clay particle has negative charge on its surface, and because of the negative charge, water being a dipole, H2O plus H2 will stick to actually minus charge of clay particle. It will get stuck, and therefore it will absorb a lot of moisture, and you can actually feel that it is smearing around your hand if that is there. So that is what actually uh, and the other question that is asked is, Suppose if you take wood that will float in water, that's an interesting question. And then here what we have to see is, suppose if you take sand, gravel, silt and clay, all these materials are inorganic in nature. That means rock would have been subjected to weathering, and that would have formed into gravel, further weathering sand, further weathering silt and then clay. And specific gravity of most of these materials will be of the order of 2.6 to 2.7. Suppose if you take the wood, for example, the basic constitution, it is a continuous material. It is not a particulate material. Particles, intermolecular attraction is there, but specific gravity being lower, it may float. That wooden material cannot be compared to soil materials whose origin are from weathering of rock. Therefore, the specific gravity is being same. Sand is going down, gravel is going down, but silt and clay particles, individual particles, are going into the Brownian motion, which you can observe by simple experiment. That shows that it is the whole material is not a gravitational material. It is surface-surface interaction, and then by chance collision, these particles will form into bigger particle, and then that will fall down after the specific gravity that the given material assumes a specific value, it falls down. Otherwise, they are all fine particles. They will be going, if you take the water which is pure, it will go into Brownian motion. That's what we have to understand. Whenever we are comparing, we have to compare with similar materials. And when you are comparing with dissimilar, for example, if you take steel, it will go down. Then we cannot say that steel is a gravitational material. It is a solid material. And if you take wood, if you take steel, if you take aluminum, intermolecular attraction will be there. If you bend it, everything will bend together. If you take particles, they actually fall apart as individual particles. Therefore, by simple experiments, by actually corroborating different other experiments also, we can logically conclude that soil is a particulate system. And this is a nice question that is Altmarsh has asked, and I think he got the answer. No, no, it is actually, if you take clay, for example, if you take river course, if you take river course, what happens is in the river course, all the boulders will be there in the upstream side. And then you see that gravel is there in the little downstream side. When river is confluencing with the sea, you can see that deltas are formed, fine sands will be there, and then clays will be formed. So what we see here also, the clay particles will go in suspension. They travel long distances along with the stream, and then finally, when the river is confluencing with the ocean, there you can see that fine deltas, fine particles, marine clay deposits are formed there. Upstream side of the river, we see that there are boulders and then the gravel, and then we have see the sand, and then when it is confluencing, that means this clay will go in suspension along with water, and then it will get deposited when river velocity becomes steady, because when it is confluencing the sea, almost it becomes horizontal. And if you take upstream side, there will be slope and it becomes horizontal. And then when it is confluencing with the sea, the finer suspension, which particles were there, uh, actually drawn by suspension, would be actually settling down later. And that's how we can say that it is a particulate system. It takes a long time to get, and the relative settlement, that is sedimentation, is one of the very important aspects. They're based on relative velocities and relative time of settlement of individual particles. Those who are settling down very rapidly can be said gravitational materials. The other materials are not gravitational materials. They may settle down after a long time, but they show surface-surface interaction phenomena, and therefore clays always have a lot of chemistry we have to study when you are interacting with clay. So how to strengthen the clay? That's another question Gautam has asked. If you want to strengthen the clay, what happens is, if you completely see that load is placed, That's what in Korea I have seen soft clay deposits. Suppose if you withdraw water from the system, it becomes solidified. I have already said the experiment that if you take clay and then go on mixing with water, it enters into solid state, solid state, semi-solid state, plastic state, and liquid state. That means clay will undergo different phases along with water. So once you want to strengthen the clay, what we have to do is apply the load and see that water is completely driven out. And once this water is driven out, it becomes stiff, and then it assumes the strength, the greater strength. And therefore, we have to do preloading technique. It is called, whenever you are building a structure in a soft clay deposit, you apply load, artificial load, and see that water is completely driven out, and after some time total water has come out, the soil would have been consolidated, and then we can construct real structure on that soil. So we can actually strengthen the soil by removing the water from the system, or by mixing chemicals like lime and cement we can mix, so that we transform the entire soil into a different type of material, and then we can do a lot of stabilization. Okay, so I just would like to tell you some example of the things that I've studied. It anyway, it is in 3 series, and then we have to quickly go through that. And what you can do is you can post me questions to my email. I will leave my email ID to Satish, the head of the department. If you have any questions, you can type me by email also, so that I would be able to give clarifications, and then you can also, if possible, when I come to the institute, I will interact exclusively to see that some of your doubts are clarified by demonstrating to you how to understand soil as a material. So what happened is, how much time we have, Satish, now? Okay, so a multi-stored building was constructed in Hyderabad in 1981. And what happened was almost the structure was complete. After completion of the structure, just before inauguration, what happened was the whole building started experiencing collapse. That means G+5 structure, after completion of the construction, it experienced to collapse. What was actually the first floor has gone to ground floor. Like that, there was a settlement of one floor, and the entire building on one side completely collapsed in 1981. And then I have actually found out the reasons for that. I'm going to present the technical features little later. And then we have water come sump. 1993 in Nellore, one agency has constructed water tank come sump in Nellore at Dargamita area. And then what happened was in 1993, somebody is actually keeping the mic open and there's the hum disturbance being experienced. So they can unmute, they can mute it so that there will not be disturbance overall. So this water sump, which was constructed in Nellore in 1993, what happened was when Nellore received bounty rainfall, the water has gone into ground, and the soil on which they constructed this water sump was a silty soil, and they have adopted the design that they have made elsewhere, and same design they have utilized for construction of some water tank sump in Nellore on a expansive soil. Then when the Nellore received heavy rainfall, then what happened was the soil started swelling, and it has lifted the entire sump. And as the sump got lifted up, all the pillars, they got twisted. When I was taken to the site, I have seen at the joints, reinforcement got twisted. Everything actually left broken. And then they wanted me to do some remedial work for that. And then when I brought the soil sample from foundation, and experienced it and found out what is this swell index and what is the swelling pressure. We found out that swell pressure is 38 tons per square meter, and the bearing capacity which they have used is 15 tons per square meter. Therefore, there was an upward pressure of more than 23 tons per square meter, which has actually lifted the entire sump and caused the entire failure of the water tank cum sump. This is actually happened in that area. There is a one question, let me take that question. How to find out the apartment G plus floors for, how to find out the apartments G plus floors for apartments? I'm not very clear about this question, but I would like to tell you that as suppose you are planning G plus 5 apartments, what happens is when you do the load analysis, per floor actually 25 tons per floor per column will be the magnitude of load. Suppose if you have got 5 floors, 5 into 25 per column, 125 tons of load will be there. And once that magnitude of load is coming, if you assume that bearing capacity is 20 tons per square meter, 125 divided by 20, it will be 6 square meters. That means we have to put a footing of 3 meters, and 3 times width of the footing we have to investigate. That means we have to go down below at least 9 meters and check the entire soil properties so that we are safe, because there is what is known as pressure bulb. Suppose if you are sitting on a ground, and once you are standing on a ground, your weight will go through the ground to some depth, and that depth is called depth of influence. Similarly, if you are constructing a structure, it will have a depth of influence. Suppose if it is a 5-story building, at least we have to go down below 20 feet depth, find out what type of soil is present. Based on the soil properties, we have to take decisions regarding what depth, at what depth we have to keep the foundation. That is what we have to do. I think the question that was asked by Sai Prakash, you have to be very careful when you are actually going for apartments. We have to go down below the ground level and investigate the soil, and then find out the properties, ascertain the bearing capacity at different depths, and whichever depth actually gives us adequate bearing capacity, we have to keep our foundation there. So this is what actually happened in water tank. The swelling pressure was more, and when ground received water through heavy rainfall, the entire soil started swelling. It has actually uplifted the entire structure. So the water tank and sump got completely broken, and it has to be demolished, the whole structure, because of the mistake that they have adopted the foundation which they have actually done for a competent soil. They have adopted to clay, which is actually swelling type, and without regard to soil properties, that has actually caused the entire problem. And then I solved that issue, and I will also tell how that problem was solved. And similarly, there is a bridge at Jonavada. You can see also now nearby Nellore, that bridge completely experienced collapse, and you can see the remains of collapse even today, because the foundation depth was within this cover depth, and during those days they have not gone through this cover to the rock bottom, and then they have not plugged, they have not grounded the foundation at bottom, and then when Penna River received lot of rainfall, all this cover it has actually undermined, exposing the foundations. The whole structure which they constructed fell like pack of cards, and that also has happened because they did not pay proper attention to the foundation aspects of a bridge, and perhaps with some kind of confidence they went ahead, and you can see the failure that has happened across the Penna River near Jonavada. Even today you can see the remains of bridge collapse. Similarly, there are many things that are there, and I just would like to present to you about the Hyderabad collapse of a building. And this is the site. They have constructed 1, 2, 3, 4, 5 blocks. They have constructed these blocks already completed, and you can see that earlier there was a nalla, there was a drain that was going for 10-20 years. This nalla was dried, and they thought that this actually completely is defunct, no more water would come here. And then what they did was they completely filled it with soil, and then they actually did the pile foundation. And then when 1981, when heavy rainfall was there, again this drain reopened, water started going through this drain. And once water was going through this drain, what happened was, whatever the piles they have installed here, this total soil around the pile completely got eroded, and then it was subjected to complete erosion and undermining. And you can see that the entire soil investigation was taken up, and then you can see that this was the building that was there before actually the collapse. And you can see the whole building got collapsed because that drain which was there, over which piles are driven, that drain completely again went with full charge of water. It undermined all the surrounding soil of the pile. Pile has lost its lateral support and completely experienced buckling, and then whole building has experienced collapse. And later on, they made a provision that any building of G+3 nature, they have to get thorough soil investigation done. And from then onwards, the complete regulations have come across Andhra Pradesh. Therefore, many structures which are constructed, they come to educational institutions for consultation or doing testing work, and other suitable agencies they approach. They get the soil tested. Once you test the soil properly, and then do the foundation design appropriate to the soil properties that are found at a given location, absolutely there will not be any issues. But as Carl Tesky said, if you don't regard the soil, the consequences of devastation will be very, very catastrophic. That's what Tesky said in 1952 Rankin's lecture. And we have to be very careful about the soil investigation and the soil nature. And depending upon the type of soil, we have to approach various methods. And suppose if the competent soil is available at shallow depths, we go for shallow foundations. If competent soil is not available at shallow depths, we have to take the foundation loads to deeper strata by piles. And if you take, for example, Chennai, Kolkata, Vizag, Mumbai, all these cities, they're all on all infrastructure projects. All buildings are on pile foundations because they're all situated in coastal area. They're all soft clay deposits. So the soils which are available at shallow depths, they are not actually having competent soil properties. Therefore, they transfer the loads to much deeper strata where they get either foam strata or rock, and then transfer the loads to the rock bottom, and then where they encounter rock, and they ground the piles there, and they construct the structure. So any decision that you take, as I said, engineers are decision makers. The decisions are based on data, and the data should be reliable data, and the data should be based on proper experimental investigation. And sometimes we do field testing, sometimes we bring the samples to the laboratory and then do confirmative testing, soil properties evaluation. All these things if you do and take proper decision, then any structure, I keep telling my students, earlier it used to be any project on competent site, now any project on any site, because we have got lot of technology that is available with us. And the only thing is we have to properly characterize the ground, evaluate the soil properties, ascertain what type of depth of foundation is required for a particular type of structure, depending upon its loads, loads that it is taking, and then we take wise decisions. And if there is any problem, we can always do some kind of treatment, either by modifying the ground, either by compaction or dynamic loading, or by using some chemicals, or by transferring the loads to deeper strata. Lot of options are available, but first and foremost thing is you should be able to characterize the ground. These are some of the things that I said. I will tell you in the next class how actually some of the technical solutions could be provided. And just to conclude, I would like to say that this is the ground profile. We have to understand the ground profile first, and then we have to use proper mathematical model or we have to apply some techniques to evaluate soil properties and then try to understand the soil behavior, and then we should be able to, based on our experience, we should be able to take decisions. So this is actually the concept of soil mechanics triangle. We have to understand ground profile, you understand the soil behavior by appropriate model, add your experience to that, and then take decisions. And we have to try, first thing is ground profile by soil investigation, and we have to describe the soil properties, then use like Ortesgy's principles or any other sound mathematical tools to understand the bearing capacity, properties, and other settlement calculations, and then understand what is stress strain, the language soils will speak. I said the language with which soils speak is, one of the languages is stress strain diagram. If you get a very straight, stiff diagram, the soil is very strong. If you get a slanting stress strain curve, that means it is a weak soil. That is the language with which soil speaks, and we can understand the soil behavior and then take decisions appropriately. So this is the soil mechanics triangle we have to understand, and by proper site investigation, we using proper theory and understanding soil behavior, adding experience and designing the foundations. Once you follow this triangle, all your infrastructure projects will be safe. Therefore, any project to have successful performance, the first thing is soil investigation. So geotechnical engineering plays a vital role in infrastructure project development. Most of the projects which I actually have been able to interact, they're all, they encompass a lot of projects, tall structures, pump houses, and then buildings, bridges, flyovers, railway over bridges, and railroads and runways, and then and we have irrigation structures. Many places I went and tested the soil, understood the soil behavior, and advised the engineering community as to how decisions can be taken, and this actually is the importance. Now I call upon R. Manohar Reddy to share his experiences. Okay. Any questions?
Yes, ma. If you are having any questions, ma, you can ask the sir. Yes, anyone having any questions, ma, you can just unmute yourself and you can ask.
Some of the students ask very good questions. I'm very happy that the students are very interactive, and that is wonderful thing for a teacher. Even a student is asking questions, that would be a fantastic interaction, happy time with students. Some of them, they raised very pertinent questions, and if you have any more questions, you can ask me.
Now in the present semester, geotechnical it is going on, sir. So that's why they are thorough with their subject.
Oh, the subject is going on
now. Yes, sir. Now for third year, geotechnical one it is going
so
on.
They
sir.
have, I think, they have.
Theoretically, now they are getting the subject, and practically you are showing all the things. So yes, that's why the bridge between practical and theory it is filled here, sir. So whatever theoretically we were discussing.
Yeah, next class maybe I will show you some more case histories, and then go into what are the causes, what are the remedies. Also, I will present. So that completes this particular series, and then if anything more is there, we'll definitely take forward in future.
Okay, sir. Sure, sir. Okay, sir.
Okay, Satish.
Yes, sir.
Hello, sir.
Hello.
Sir.
So please tell me.
Thank you, sir, for joining with for presenting a valuable lecture to our students, and for being patient regarding our student doubts also. And from our chairman, sir, as well as from our principal, sir, we are very much thankful, sir, for today. And This session will continue for tomorrow and day after tomorrow also.
Yes, 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 yes.
Yes, sir.
So
And
just give me feedback, and so that how students are actually taking the lecture and interaction program. You
okay,
can
sir.
also write to me this feedback, compiling the feedback from students.
Okay, sir. I'll get it, sir.
There is one question. Let me see.
Okay, sir.
No, somebody asked, Leaning Tower of Pisa has collapsed, whether it is still present. So, no, it has not collapsed. It is only, it experienced a lean. I have seen 16.5 feet from Plumbob, there is a lean. It only experienced, that's why it is called Leaning Tower of Pisa. And then what John F. Burland did was, he found out the reason. Until then, they were practicing some empirical methods. And Burland found that there was some stream somewhere, and through the stream, what was actually finding its way to the foundation, he has cut that source, and then it has started becoming dry, and then that lean now has been stopped, and it is still there as a leaning tower of Pisa. It has not collapsed. It is still there. It's a major attraction. People go and see that, and they find that kind of experience. World famous structure. Still, it is there. It is safe. Only thing is, it showed differential settlement. One side soil is very strong. The other side it is weak. It has tilted, but the tilt has been arrested. Now it is stable. No.
Okay, sir. Sir, the feedback is that the students are very much interested, and actually they asked questions also, sir, for you.
Yes, yes, yes.
Why means actually they participated, and they are very happy, sir. And some of the messages we got that, sir, we are very much thankful like that to the principal, they said, and as well as to the chairman, sir, also.
They said, okay, thank you. It is my pleasure. Somebody has thanked already. But anyway, it will be nice time. We'll again meet tomorrow.
Yes, sir. Okay, sir.
Bye, Nana. Bye, bye.
Thank you, sir. Bye, sir. Thank you to all the students, and tomorrow again we'll join the session. Thank you.